In this video, I'm going to show you how to derive the Fourier coefficients. In the last video, I showed that this was the goal of Fourier series, right? Was to be able to solve for a sub naught, a sub n, b sub n, and then plug them back into this, and this would be our final answer for our PDE. But how do we get a sub naught, a sub n, and b sub n? Well, let's start with a sub naught. Solve for a sub naught, we're going to basically just integrate both sides of this equation. Now let's say, before we begin, let's say that f of x is a piecewise continuous function on negative L to L. L can be anything. And then the period would be 2L. Right? To find a sub naught, we're going to integrate the left side. And then we do the same thing on the right side. Let me do this. Dx, right? So what we can do, I'm just going to set equals, right? We'll have the integral of a naught over 2 dx plus the sum n equals 1 to infinity of a sub n. That's a coefficient, right? So you can pull it out. Negative L to L cosine n pi x over L dx plus bn integral negative L to L of sine over L dx. We can integrate the first one. That's just a sub naught over 2 times x from negative L to L plus the sum of a sub n times let me think about this. We're integrating, so it's L over n pi times sine n pi x over L from negative L to L minus, because the integral sign is negative cosine, L over n pi cosine n pi x over L from negative L to L. Doing this, we'll get a sub 0 over 2 times L plus L plus the sum a sub n L over n pi times, that'd be sine n pi L over L, I plugged in for L, right? Minus sine of n pi negative L over L. That's just 0, but hold on, let me continue. I guess be minus b of n. I'm out of space, of course. Doesn't matter anyways. This is, you're gonna see what I mean, times L over n pi times cosine n pi L over L minus cosine of n pi L over L, well, negative L. So now we're here, this will become a sub naught over 2 times 2L, which is just a sub naught times L, plus sine of n pi minus sine of negative n pi minus b sub n cosine of n pi minus cosine of negative n pi. Now remember, cosine is an even function, so it doesn't matter what's on the inside of the cosine. So let's say, for example, n is equal to 1, right? If n is equal to 1, then cosine of pi is 1. Cosine of negative pi is also just going to be 1. It's an even function, right? 1 minus 1 is 0. So because cosine is an even function, this whole term is 0. Now let's plug in n equals 1 in for the sine term up here. If we plug in 1, sine of pi is, what's sine of pi? It's 0, right? And sine of negative pi is also 0. So that'll be 0. That's 0 times all of that. This one's 1 minus 1. This becomes, yeah, you can say it's 1 minus 1, for example. That's why it becomes 0. But anyways, all that we're left with is our f of x dx is equal to a naught L, right? So now just solve for a naught. So a naught is equal to 1 over L times negative L to L f of x dx. And there you have it. There's a sub naught. That's the setup for a sub naught. And then we would go ahead and plug in our f of x and the subinterval that it's in, and then solve it. All right. Now let's look at the next one. So let me go ahead and copy this again. And now we're going to look at a sub n. Okay, so for a sub n, we're going to take cosine now and multiply it by f of x. So we're going to have f of x times cosine n pi x over L. And of course, we're going to integrate it from negative L to L. This one's going to be a little long to write out here. I'm not going to probably fit it in one line. I don't think so. L, a naught over 2 times, well, yeah, times cosine of n pi x over L dx plus, and I'm going to split these integrals up. Let's see. Okay, I'll put them down here. Oh, well, I forgot the summation though. I'll put it up here. Oops. a to the n cosine. So it's just going to be the same thing. Oh, hold on 1 minute. I completely forgot. When we do this, the cosine that we multiply everything by, we're going to use m instead of n. As you can see why. There's going to be a different value for that cosine, right? M still being 1, 2, 3, n still being 1, 2, 3, and so on and so forth, but we just have to do differentiate the difference, that there's a difference between n and m. Let's look here. But there is also the chance that n could equal m. And I will show you what that means in a minute. But actually in like 2 seconds. But let me write this out first. I can pull that a sub n out, right? Because it's a constant. Negative L to L of cosine n pi x over L. I'm sorry, sine, right? Times cosine. I'm sorry, yeah, cosine m pi x over L. dx. So we have all this to work with. Now we're gonna look at I guess 2 cases, right? Well, let's do this. Let's look at it for a case when n does not. Let me do this first. When n does not equal m. Let's just look at the a sub n term. Let's just look at this over here. Let me copy this. And I'm going to show you what happens when n doesn't equal m. So if n doesn't equal m, I'm going to show you a bunch of trig identities here. If you have cosine of a plus b, that is equal to cosine of a, cosine of b, minus sine of a, sine of b, right? Cosine of a minus b is equal to cosine of a, cosine of b plus sine of a, sine of b, cosine of a plus b plus cosine of a plus b would be just 2 cosine a cosine b, right? Got that from this one up here. If you add 2 of them together, yeah. Anyhow, well, there's more to that one, isn't there? 2 cosine a cosine b minus 2, right? And this is just looking at the at this one, right? So if we're looking at integrating this, you can rewrite it. So, well, we don't even really need this one necessarily. Well, yeah, we do. Yeah, I suppose we do. Well, that'd be sine A, sine B. What am I doing? So we have a n integral negative L to L cosine n pi x over L cosine m pi x. Well, I want to do this. Remember, m pi x over L. I'm using sorry, that would be it. I'm using this one here, right? The 2 cosine A cosine B one. You can add them insides together, so that's plus the same exact thing. Cosine A plus B, which it would be literally rewriting the exact same thing down. Oh, that's supposed to be minus. That's the difference. That's the difference. Yes, okay. My bad. I had a little sign error there. That's why I was confused. It's cosine of A minus B. That's why you add these two together. And these two cancel. You're left with 2 cosine A cosine B. Okay. Yeah. Plus cosine of n pi x over L minus n pi x, sorry, m pi x over L. These two added together. So what we would be left with would be, let me look. Just like before, when we integrated the cosine and we got the sine, where do we do that? Over here we got the sine, and then we sine of n pi, any sine of pi. So this, if you look at these, it's still in terms of pi, right? It'll just be like n minus m times pi, the cosine of times pi x over L. So still in terms of pi. If we integrate that, we'll be left with a sine that's in terms of pi. If you have that, this term will drop off. And so would this term would drop off, become 0. So every term's going to drop off. And if you're looking at the sine part, the same exact thing would happen. The exact same thing would happen. Let me write it down. In this case, we're going to use different trig identities. Right, we have to use the fact that was the sine A plus B is equal to sine of A cosine of B plus sine of B cosine A, and also sine of A plus is equal to, so A minus B is equal to sine of A cosine of B, and then just flip the sign. Right? Of course, if you put those together, you left with that would be, let me see, those two would cancel. You're left with sine, 2 sine A cosine. Oh, also I forgot about that 2 there. If you do do that identity there, we're gonna have to divide it by 2, right? My bad. So in this case, we can rewrite that where we have sine of n pi x over L times, also that's 1/2 bn times, I'm sorry, minus, plus m pi x over L plus sine of A minus B, well, and in this case we'd have terms that are left with like n plus m pi x over L, and if we integrate that, we'll have some cosine times some crazy thing like this, right? But if you were to plug in Well, this cosine is, remember, an even function, right? And it'll be what, minus. You get my point. No matter what, it would end up being 0 because cosine is an even function. Whenever you have and it'll be minus the L, so that term will go. It'll be like this is. I'm just looking at this first one here, and this would be L. This would be cosine, something like this, right? Doesn't have to be exact as long as what's on the. I'm just going to show what's on the inside. Ignore what you're going to multiply by. That doesn't matter in this case. Just to show this, if we had something like this, this is basically the same thing. Cosine is an even function. So whatever's on the inside can also be positive, right? And guess what? Those are the same exact things. That's 0. So you can see how they just subtract from each other. Same thing would happen with this one over here. So every term would drop off again. Drop off. So we're not going to look at this case anymore. So we don't need this, right? So now let's look at when n is equal to m. So when n is equal to m, that's an n by the way, we have, let me go ahead back up here before this and let me copy all of this down and paste it back down here. If we were to do this, we can basically just replace I'll replace every m with an n. I'll do that. Replace every m with an n. And then we can rewrite this whole thing then. So this would become, you know, the integral negative L to L cosine n pi x over L dx is equal to negative L to L of same exact thing again. I can move that bar there. I separated them. A naught over 2 cosine of plus the summation n equals 1 to infinity of a plus n a n negative integral negative L to L. This would now be cosine squared n pi x over L plus b sub n integral negative L to L. Oh, that wouldn't simplify. Well, this one would be cosine squared. This one over here would be and guess what? Remember the little trick I just showed you in the last thing where we have to use the same exact thing, right? In this case, okay, let me do it. Let me do this out. I'll show you. First of all, I'll show you what happens to this b of n term. I'll show you how this one disappears. Let's look at this first. We're going to use that formula that I just, let me recopy this down. Where is it? We could use it this way. We could probably do another way. I don't know. But I like to do it this way. We would be left with b sub n integral negative L to L over 2 times, just like before, sine this case, we have n and m, so they would combine, and we're left with 2n pi x over L. Yeah. And if we look at the other term, so I should have, here, let me do this. You still see that, right? And then I want to look at the other one. I'm going to move it over to here. Do this one over here. That's going to bother me. Okay. This one would be a sub n integral negative L to L. We would use a half angle identity, right? Because it's cosine squared. It's even power. That'll be 1/2. So we multiply. So this, take out the 1/2. Sure. That would be cosine. Well, it'll be 1 plus cosine of 2 n pi x over L dx. Plus this, of course. So I already know where this is going. I can tell you that this sine one's going to drop off because we're going to have cosine. Remember, it's going to be an even function once again. I'll show how it goes. I guess that would be L over 2n pi times sine cosine if we were to plug L into there, we have cosine of 2n pi x minus, and that would they just cancel out, right? They're exactly the same. Cosine's even function, so no matter what, if you plug a negative in there, it's not going to matter. It'll cancel, right? It'll end up being 0 plus 0. Well, actually, it'll end up being not necessarily 0 plus 0, but no matter what n term you plug in there, you're going to end up with the same number minus the other number. So like it'll be like an n minus n is what you'll be left with. Well, you'll be left with the cosine of n minus the cosine of n. No matter what basically that's what you got to look at it like that. So that term drops off, goes to 0. We no longer need this one. I'm going to go ahead and take this down to here. And I'm going to go ahead and integrate that. That'll be what? X plus L over 2n pi times sine of 2n pi x over L dx. Sorry, not dx. From negative L to L. Oops. So now we have an over 2 times L plus L over 2n pi sine of 2n pi L over, which is just that, minus, so plus L. Let me do this. So plus L minus L over 2n pi sine of negative 2n pi so that would simplify it to this, but the thing is I don't have to really worry about it, because for any value of n, 1, 2, 3, and so on, that sine of pi is 0, sine of 2 pi is 0, sine of, if you plug in 2, sine of 4 pi is 0, plug in 3, sine of 6 pi is 0, so it's not going to matter. These terms are going to drop off. And you're just left with an over 2 times 2L. So then this is just an, oh sorry, I should not have erased that. So then this is just an times L, and we still have this. Oh boy. Here, right, is equal to an sorry, why did I just erase that? An times L. So then an is equal to 1 over L integral negative L to L f of x cosine of n pi x over L. So now really quick, just looking at B sub m, B sub n is really going to be easy now, looking at it. So all this is, you just do like the same exact thing basically as we just did. This case we're looking at sine now, so sine this will still be cosine, this would be sine, this would be sine. So all that's going to change is we look at n equals m. Just like before, we have the integral negative L to L. The exact same thing is going to happen with the cosine times sine, right? It's the exact same integral that we have right here. Exactly the same. It goes to 0. So we know this goes to 0. We know this one up here goes to 0, right? Because just like before, where is it? Oh, did I forget to show that? I may or may not have forgotten to show that. But it does go to 0 because it's going to be sine. And of course, any number you plug in for n, sine of pi is 0. So that goes to 0. I should have stated that, right? I forgot to. So then we're just left with this one. Sine squared, right? So b of n, negative L to L, sine squared n pi x over L. And if n doesn't equal m, we'll get the same thing. Every term will drop off. You can go through it if you want to. For time's sake, I'm just going to do it for this. So now we're left with this times another half angle. This one is what? 1 minus cosine of 2n pi x over L. Sorry, the integral's still there. Is equal to bn over 2 times, that'll be L, let me write the integral, x minus L over 2n pi, integral of cosine is positive sine, yep, sine of 2n pi over L times x. We have okay, so we have our bounds. I had a little brain fart there. Negative L to L. We have our bounds. This is b to the n over 2 times L minus L over 2nm sine of 2n pi L over L, which is just 2n pi, minus, so plus L minus plus L over 2n pi times sine of negative 2n pi. Doesn't matter what's on the inside. This will be 0 for any n, and this will be 0 for any n. We're left with bn over 2 times 2l. So that's equal to bn times l. If that's the case, then we are left with, where do I have it? Right here. This is equal to bn times l. So then bn is equal to 1 over l times integral negative L to L of f of x sine n pi x over L dx. So, quick little recap. So, when you're solving your Fourier series problems, you can skip all of this. I just wanted to show it. And you can just use these formulas. I would 100% want to skip all of that because it's useless to do it every single time. A sub naught is 1 over L. 1 over L times integral negative L to L f of x dx. A sub n. Actually, before I do the recap, let me copy our goal down here. So for a recap, we have our goal and then our coefficients. Now that we have them solved, a sub n would be, it was 1 over L integral negative L to L f of x cosine of n pi x over L dx. Our b sub n was 1 over L integral negative L to L f of x sine of n pi x over L dx. We would then, based on the given conditions, or we would know what our bounds would be. We would know what our length would be. The length is just half of a period. And I'll show you all that in the next video when we do Fourier series, but yeah, and our function would be our function in that bounds. So sometimes we may have a piecewise function where we have this from, say, 1 to 3, and say the next one's from 3 to 4. So you're gonna have to add up those two integrals, right, for the function that follows in the subintervals. So these can get very long. I'm sure you might have heard or have already seen, but these problems do get pretty long, and that's why we skip all of this stuff and we just kind of want to memorize these. So you might want to memorize these. Anyways, Next video, we're going to look at Fourier series and everything that entails, and do some examples, of course, with piecewise. We're going to look at like piecewise functions, like I said. So it's going to be a little bit longer. It's definitely going to be a long video. I might have to break it up into an example per video. So I'll see you in the next. I'll see you for Fourier series.